Happy Friday, everyone. Welcome to our latest deep dive into the fascinating world of cable technology. I'm Brady Volpe, founder of the Volpe firm and chief product officer of OpenVault, your host for today's journey beneath the surface, exploring skin effect and depth in coax cables and other plant devices. We're set to unravel some of the more elusive yet critical aspects of network performance. As always, I'm joined by the esteemed Ron Hranac. He's a treasure trove of knowledge and experience in the field and also a 51-year veteran of the cable industry. Please be sure to check out Ron's full bio in the YouTube description below, as it is quite impressive. Today we're zeroing in on the skin effect and skin depth, a phenomenon that might seem abstract but have real tangible impacts on our coax networks and devices. Whether you're a field veteran or just embarking on your technical journey, today's session promises to shed light on these complex concepts in an accessible way. Ron, it's fantastic to have you here again, ready to help us peel back these layers.
Hey, Brady, thank you very much for the kind words, and Happy New Year to you, and Happy New Year to everyone who's tuning into either the live session or a replay a little bit later after this gets posted on your YouTube channel. And as you say, we're going to, I love your almost Dr. Dad joke hints there about getting under the skin or something. But yes, we're going to do that today and talk about something that is really important and, as you know, kind of abstract from one perspective, but I think it's helpful to understand. So let me bring this up and we'll start right here.
We'll dive right in. And folks, if you've not already, please do subscribe to our channel and definitely give us a like if you like the content. And be sure to drop your questions into the live chat if you're joining us live on the live stream today.
Yeah, so here's the title slide to the slide deck that I'll be using today, and I've got some illustrations in here that hopefully will communicate the concept of skin effect and skin depth. And as Brady noted, these are phenomena that apply to pretty much the entire coaxial portion of our cable networks. So that's the cable, the passives and active devices, anything that has RF on the inside definitely has a relationship to what we're talking about today. I'll focus more on how this impacts coaxial cable, but the principles apply to pretty much everything else. So with that, let's go ahead and get underway here. The skin effect then is a really, really important part of the coaxial part of our networks. And you see a graphic there of a piece of coaxial cable, but as I said, the principles apply really to everything. So a piece of cable here and drop cable, hardline splice. Okay, now this one won't shield things very well, but it's a cutaway. Even stuff like our passive, so taps and things. All these have a piece and part that's related to their performance by skin effect and skin depth.
And I think that's important, a skin effect, because I think you and I had even talked about that before. A lot of times we think skin effect only impacts the center conductor of coax cable. And so for this session today, it goes a lot beyond just the center conductor of coax cable.
Oh, yeah. It applies to the shield too, and we'll talk about that. I'll be focusing at least for the concepts on this on the center conductor, but the same exact principles apply to the shield. They apply to the housings for taps and directional couplers and other passives and connectors and splices and amplifier housings, everything. So there's an important role that skin effect and skin depth play in RF shielding. You might look at a piece of coaxial cable like the graphic on the screen or this piece of 750 that I'm holding here in my hand. What keeps the RF inside? We say, well, the shield keeps it inside. But the question might be, well, why? And part of that is related to skin effect. It helps to ensure that the RF that we want to carry in our network stays inside those cables, and that the RF that's in the over-the-air environment stays outside the cables. Right. Because that same principle of skin effect also works on the outer surface of the shield of the cable. It works on the inside surface of the shield of the cable, and it works on the outer surface of the center conductor. So that, of course, all depends on the shielding integrity being intact. If you've got squirrel chews or radial cracks or loose connectors, then all bets are off. But as long as the shielding, if the shielding's not damaged and it's doing what it's supposed to be doing, then skin effect plays a big role in helping to keep the RF inside of the coax part of our plant. Now, it also plays another role in something that we all see every day in our dealings with coaxial cable, whether it's hardline cable or drop cable, and that is we see variations in attenuation versus frequency, and as the frequency increases, so does the attenuation per unit length. And say, well, why the heck is that? And we're going to talk about that today, and that applies to hardline cables and, of course, drop cables. But let's start with what goes on in the world of direct current. Direct current, of course, is what you might get out of a flashlight battery or the battery in your car. So let's consider an electrical conductor that's carrying an electric current, but it's carrying direct current. So for direct current applications, let me get this little guy out of the way here. The entire cross section of the conductor, so visualize the center conductor, in this case, of a piece of cable, but the entire cross section at DC is what carries the current. Whoops, that's probably the noontime spam. Yep, it is.
We'll get that later.
I just hung up, pick up the phone and hang it up. So anyway, so the entire cross section is conducting current, and I used little asterisks here in this cross section to represent what could be the electrons or holes, but usually electrons, representing the entire cross section of that conductor carrying the current. But when we get into the world of alternating current, and it's important to understand that alternating current, or AC, includes RF. So the conduction of the current, when you get into the world of AC, is largely confined to the outer surface and near the surface of the conductor. So here you can see that in the cross section of this wire, when we get into alternating current applications, you see where all the electrons are. They're traveling primarily at and near the shield or at and near the surface of this conductor, and you don't see anything in the center. And that has to do with what we're talking about today, skin effect and skin depth. Now, interestingly, the higher the frequency, the shallower that region where the conduction occurs. And that's the phenomenon that we call skin effect. And we'll talk about the why here in just a little bit.
So couldn't manufacturers create, save money by having basically hollow core center conductors on the coax cable?
That wouldn't be real practical in the cables in our networks, but if you go to a broadcast transmitter site, you'll see that they oftentimes use really large diameter specialty coaxial cable that's made for carrying many thousands of watts of RF power.
Very high
and
power.
If you look at the center conductor, it is in most cases a hollow copper tube,
right,
and it works just fine. So yes, it is used in some applications, but just not in our networks. But it does get to another point we'll talk about here in just a little bit that's related to the composition of the center conductor in our cables. Now, an important piece that's related to skin effect is known as skin depth. And it's generally referenced by the Greek letter delta, the lowercase Greek letter delta. And that's a measure of skin depth. And it is defined as the depth at which the current density is 1 divided by E of the current density at the surface of the conductor. So there's an example. I understand that the graphics I've got in here are not to scale, but I've really made them to illustrate what's going on. So we can see here that this little region at and near the surface is what we call delta, or the skin depth. And you say, well, all right, 1 over E, what the heck is E? Well, E is a mathematical constant, and you may remember this from math class way back, but that is the natural logarithm, which is equal to about 2.7. So 1 divided by E is 37%. On my scientific calculator here up near the top, there is a button marked LN. That's the button for natural logarithm. So that's where that comes from. So that defines the skin depth in a metallic conductor. But it's important to understand that alternating current through a conductor doesn't stop at that dashed line. If you note, when I created this, I tried to get the shading of this to fade gradually the deeper into the conductor. And the reality is that it decreases logarithmically with respect to the depth, and the conductor doesn't stop right there. But the bulk of the current is within that skin depth region. And there's some math.
we're gonna get deep into the math now.
Now, there's no test. You don't have to remember the equation.
Okay.
It's about to come up. But I want to show you that, in everything we do in cable, math is important. And I know techs in the field is, I don't need no stinking math. Well, you do, even if it's addition and subtraction, where you're subtracting, loss through a splitter or adding gain through an amplifier. You're using math, but you may not have to use this kind of math. So there is one of the equations that can be used to calculate skin depth. And again, there's no test on this. You don't have to remember this. But here you can see all the terms that get plugged in, like the delta. There's your skin depth, in this case in meters. And you say, well, wait a minute, we're not using conductors that are a meter wide. But of course, you have to chop that down into smaller chunks. Rho, and that's this little thing that looks like a P, is the resistivity of the conductor in ohm meter. Now, when I say ohm meter, that does not mean the ohm meter that you're using to measure DC resistance.
Not a voltmeter.
It's not. And people say, well, what the heck is resistivity? Don't you mean resistance? And not quite. They're related, but not quite. So when people talk about resistivity in metals, the way to visualize how that is determined is to imagine a solid cube of metal that is 1 meter by 1 meter by 1 meter. Whether it's a solid cube of copper or aluminum or steel, whatever it is. When we talk about the resistivity of that, visualize this 1 meter by 1 meter by 1 meter solid cube of that metal for whatever it is. And then you put 2 plates on opposite sides of this, and you measure the resistance between those 2 plates. And the number you get is called the resistivity of the metal. So if you look at the resistivity of copper, it's really a small number, as you might imagine. Yeah, copper is a really good conductor.
Yep.
So if you visualize this 1 meter by 1 meter by 1 meter solid cube of copper, its resistivity measured from one side of the cube to the other is about 1.6 times 10 to the minus 8th. That's a real small number.
Almost negligible.
Well, it is, but
it's measurable, but very tiny.
You have to plug it into the formula, and then you've got frequency, and there's pi in there, and permittivity of free space, and the relative permittivity of the customer. For copper, that's nearly 1, but you plug this number in, and you say, well, all right, Ron, why are you showing this? And I'll say, well, I want to show you because there is math involved, but the good news is there's some real cool websites out there that will calculate skin depth for you, and you don't have to know this. But this is what's going on under the hood of those calculators that do that. So let's start with 60 hertz. That's alternating current. For those of you in the Americas, 60 hertz is the frequency of the AC outlets, electrical outlets in our living rooms and bedrooms and kitchens and stuff. If you're in Europe and elsewhere, it's 50 hertz, but so really low frequency, but it's alternating current. So in a copper conductor, the skin depth at 60 hertz is about 1/3 of an inch, or 8 millimeters. Out of gigahertz, skin depth in copper is only 0.00008 inch.
Very, very,
yeah,
very
it's really
small.
Right?
so it's just on the outer crust of the center conductor at that point.
Well, or the inside surface of the shield of coax.
Oh, it's depending on whether you're looking at,
or the inside of a housing for a passive or active device. It's not using very much of that depth in that metal.
And so, on a couple slides ago, you mentioned E and the natural log, and I think what we're seeing here, there is a logarithmic, easy for me to say, a natural log relationship of the frequency to the skin depth. And if you've ever seen that plotted, it has like a sharp curve. So the higher in frequency you get, the less of the center conductor or the outer shield that you're using on that skin. That really gets under my skin.
I've got some graphics later on that really help to illustrate that, particularly at RF. Now, I put together this table showing skin depth in micrometers, and a lot of people call micrometers microns, but the official term is micrometer, and that's 1 times 10 to the minus 6th meter, so pretty small number. So you can see here, I've got values from 5 megahertz up to 1.8 gigahertz, and we'll just look at the skin depth in inches. And at 5 megahertz, the skin depth is about 1/1000th of an inch. That's it.
Yep.
1/1000th of an inch. So it's gone from 1/3 of an inch at 60 hertz to about 1/1000th of an inch at 5 megahertz. And then at 42 megahertz, the upper frequency boundary of a subsplit return path, we're at roughly 4/10,000ths of an inch. At the bottom end of channel 2, we're just a little bit less than that, 0.00034 or 35 if you do some rounding there. Inch, 100 megahertz, we're down to about 2.5/10,000ths of an inch. 750 megahertz, now we're way down there. It's getting thinner and thinner and thinner where that RF is traveling. 750 megahertz, we're talking 0.00009 inch. 870, a little bit less, just under that 0.00009 or 0.87 or that 87. 1.2 gigahertz, now we're down to 0.00007 of an inch, and 1.8 gigahertz, a little bit more. It's real thin, 0.00006.
Yes, not much we're using at that point.
No. So. Now, there's something I want to mention here, and for people who have perhaps worked in the power industry or know somebody who does, or as a family friend or relative who works in the electrical power industry, you may have seen high voltage transmission lines where you've got multiple phases, and you'll notice that in many cases, instead of one big conductor for a phase, there might be 3 conductors. They're close together and then separated by some little spacers. And you say, well, why would they do that? And the answer has to do with skin effect. If they were keeping in mind that at 60 hertz, the skin depth's a third of an inch, well, you got a 4-inch diameter conductor, you're wasting all that copper.
Right.
Because at 60
it's
hertz,
running on the outside.
It's going to travel at, in the outer third of an inch roughly. So what they do is for a given conductor path, if you will, or phase on a high voltage transmission line, you might have multiple parallel conductors, and they're taking advantage of efficiency gained by using smaller diameter conductors, so you're able to use more of the cross section of each of those conductors as opposed to one great big one. So that's why they do that. And now, of course, people will be out driving around somewhere and say, oh, wait, there's a high voltage transmission line. And yeah, on a phase, there's like 3 conductors there. And now that's why they do that.
Yeah. So that's interesting. I did not know that on multi-conductors for the transmission lines. So in the chat room here, Striker350, hi, thanks for tuning in. And Patrick, good to see you as well. And you mentioned there's always pi, and Striker, you say there's always pi, referring to the equations that Ron put up. And I think that's a really interesting observation. So I know I've talked with another colleague before. Pi is so integrated in so many things that we do, so many equations, so many things in the world. I find pi such an interesting aspect of everything that we do. So yeah, keep an eye on pi, guys, because it's everywhere. It's in everything we do. It's such a fascinating part of the world and everything we do. And then Ron Stryker goes on to ask, is there any advantage of using a pure copper conductor over using copper-clad steel? I've noticed lots of suppliers not offering pure copper coax in hard lines.
And as we're going to talk about, that's a great question, and we're going to talk about that a little bit later on.
Yes.
If you can use pure copper for, say, a center conductor, but it drives up the cost because that copper center conductor is not carrying all of the RF across the entire cross section of the conductor. So you're basically wasting copper. So take advantage of the tensile strength of steel to hold up that drop cable better, and then put copper cladding on top of the steel. The RF is traveling through the copper cladding. It's not traveling through that steel. Steel is real lossy compared to copper. So
but it's strong. Steel is strong, unlike copper, which is soft.
Oh yeah, yeah. The same thing applies to the copper-clad aluminum center conductor in our hardline cable. Same thing. Yes, there is solid copper center conductor cable available. That's usually used in applications where you're transporting electrical power through the cable network, and you want to reduce the DC loop resistance a bunch. Not many operators use it anymore these days, and there are some power conductors out there, the coax power conductors, where maybe a centralized power source is used at a node, and then you're taking that out to other sites where you're distributing the, say, 60 or 90 volts AC in the plant, and that may be a solid copper center conductor, and it's also much bigger diameter. They go to lower impedance, typically around 30 ohms or so. And even if they use a copper clad center conductor for that, the increased diameter reduces the loop resistance. But no, there's no practical reason in most cases, at least if you're just dealing with RF, to use solid copper. It's just
Right.
it's basically a waste of money. That's what it boils down to. Okay, now let me get this out of the way. There we go. We talked about the equation and the math that's involved in calculating all this, and you really don't have to memorize that formula. But here's a link to a good website that's got a skin depth calculator on it. I've used this calculator before. Easy to use, and it'll spit out the answer for you. And of course, if you want to do the manual calculations, you're welcome to do it. But this is one of probably several good websites out there that'll do skin depth calculations for you. All right, then we talked about the fact that the skin depth decreases as the frequency increases. You might wonder, well, why? Yeah, the formula shows that happens, but why? What the heck is going on physically inside the conductor when alternating current is passing through it? Why doesn't it use the entire cross section? Well, here's the answer. Now, the graphic on the right, I cribbed from Wikipedia, as long with the explanation here. It's one of the better explanations that I've seen out there. But the simple reason is that AC, whether it's 60 hertz or 50 hertz for the electricity in your house, or RF, the reason is that alternating current basically induces eddy currents in the conductor that help to oppose the flow of the current going through the deeper parts of the conductor, and helps to reinforce the current closer to the surface of the conductor. So you look at the explanation here that I ripped off from Wikipedia, and I'm giving it credit. So imagine an alternating current flowing through a metallic conductor, and that's represented by the letter I right here. So these red arrows going up in the diagram will induce a magnetic field H. That's normal alternating current behavior. So we got these blue circles here representing the magnetic field that's induced by the flow of the alternating current through this conductor. Well, as the magnetic field increases, and visualize current in alternating current, you've seen sinusoidal waveforms representing voltage. You can use sinusoidal waveforms to represent current. So as that current changes, the magnetic field changes, and as the magnetic field changes, it induces eddy currents, which are basically little circulating currents here that do this thing right here. And as you can see, based on the way those eddy currents are rotating, the ones closer to the surface are rotating in a way that the current closer to the surface of the conductor are reinforced, while as that eddy current spins around, now it's pointing down, and it is opposing or partially canceling the current in the deeper parts of the conductor. So that's what's going on at the physical level to cause this phenomenon known as skin effect. And then, of course, we use skin depth to measure how deep in the conductor that skin effect phenomena is. So that's the under the hood stuff, and why the heck it's happening.
So basically, a long explanation for RF is still staying on the outside of the center conductor.
Well, yes, it stays on the outside of the center conductor. It stays on the inside surface of the shield, and then stuff in the over-the-air environment, let's say common mode currents that are induced, however, travel along the outside surface of the shield of the coax, and they stay there for the same reason, because of skin effect and skin depth.
So, comment from Jared: does the waveform matter? Like, are there any differences in 60 hertz using our quasi-square wave power supplies? So a sinusoid versus a kind of a square wave, or maybe even a triangles type wave. Does that?
No. Yeah. It's the frequency. Now, of course, if you think about a quasi-square wave, it's got higher frequency components. So it has odd harmonics? You got the fundamental and then odd harmonics with that quasi-square wave. And you can plot that on a spectrum, or see them on a spectrum analyzer. So that says that those higher frequency harmonics would be at somewhat slightly lower depths than the 60 hertz component of it. But yeah, it's a function of the frequency and the fact that it's an alternating current.
And then,
so good
and
question.
Then something else, Ron. So, I think most people or the way I would envision it is the RF signals come down and hit the coax cable and just bounce right off of it. But it sounds like the way you're describing it is RF signals could come down and couple onto the
Yeah.
outer connector or the outer shielding of the coax,
Oh, yeah.
and then ride right along that outer shielding, maybe all the way to where there's an unterminated connector, and then they could even get onto the center conductor because they're riding right along that outer shielding. Is that actually possible?
What you are describing is exactly how ingress works. That
Wow.
is the mechanism. So, an RF signal, whether it's coupled via a physical connection to something, let's say a neutral bond at the house, or whether it's induced, that the outer surface of the shield of the cable is acting like a long wire antenna. So RF traveling through the air will induce a current on the outside surface of the shield, and that current will propagate on and near the surface of the shield, the outside surface of the shield, as a common mode current. It'll eventually dissipate if there's no shielding break. But as soon as you have a shielding break, like a ring crack or squirrel chews or loose connector or whatever, that common mode current will enter the coaxial cable and become what's known as a differential mode current. And now it's propagating through the coaxial cable, the electromagnetic field through the dielectric, and the current on the inside surface of the shield and the outside surface of the center conductor. So Brady, what you described is exactly how ingress happens.
Perfect.
That's the mechanism behind it.
Well, I'm going to take my razor knife then, and I'm going to cut this stuff off the end of the coax cable here and put a connector on here so that doesn't happen.
Yeah, well,
and you can tell me why later that's a bad idea.
Well, yeah, we can talk about that later. All right, now we've talked about this phenomenon called skin effect and skin depth, and how the skin depth decreases as the frequency increases. But there's another piece to this whole puzzle, and that is the impact of skin effect on coaxial cable attenuation. Now, the chart you see here is one that I created in an Excel spreadsheet. I just took the published frequency versus loss per 100 feet, dB per 100 feet from a manufacturer's published spec. So this is for half-inch hardline cable. So this chart is based on real coaxial cable. And you wonder, well, why doesn't the attenuation just stay the same at all frequencies? Why does it get worse or get higher at higher frequencies? And you see here at 3 gigahertz, we're talking 5 dB per 100 feet. At a gigahertz, we're about 2.5 dB per 100 feet. And down here, a couple hundred megahertz, we're about a dB per 100 feet in half-inch hardline cable. So the question is, why does the attenuation of cable get worse as the frequency goes up? And we're going to find out. So the first thing we want to do is look at the major factors that affect attenuation in a piece of coaxial cable, a drop cable or hardline cable. And a great explanation can be found in the book Modern Cable Television Technology, 2nd edition. And there's a good discussion in there. And it says that attenuation as a function of frequency is related to 4 factors. So radiation out of the cable due to imperfect shielding. So think of a radial crack or squirrel chew or something else. Resistive losses in the cable conductors, so in the center conductor and shield. Signal absorption in the dielectric. And then signal reflection caused by mismatches, impedance mismatches between the cable and terminations, or pieces and parts connected to the cable, so taps, connectors, amplifiers. Even the cable itself, the physical dimensions of the cable do vary microscopically throughout a length of cable, so that results in the impedance not being perfect. But I got to tell you that the manufacturers have done a lot, starting in the 90s, with making the impedance much more uniform versus length, so that becomes much less of an issue. So the big bugaboo here is resistive losses in the cable conductors. If we assume that, let's assume that our piece of cable doesn't have any cracks in it or squirrel chews or anything else, so the shielding's not an issue. We'll assume that the uniformity of the impedance is quite good, and we can assume, just for this discussion, that the impedance match of taps and amplifiers is quite good, so that becomes a negligible part. Signal absorption in the dielectric does play a role at higher frequencies, but the big contributor to the reason that attenuation increases as the frequency goes up is resistive losses in the cable conductors, so the shield and the center conductor. So I want to talk about that in a little bit more depth, and I've got some graphics that will help to illustrate what the heck is going on here. So if we think about resistive losses in a metallic conductor, skin effect, which we talked about earlier, means that the effective cross section of the conductor is less for alternating current because most of the current travels on and near the surface. We talked about that part already.
Right.
Now, as the frequency goes up, the skin depth goes down, or that is, it decreases. So it makes the effective cross section of the conductor even smaller. Now that increases the RF resistance as the frequency increases, resulting in greater attenuation at higher frequencies compared to lower frequencies. And in fact, you could visualize, and we'll just pick on a center conductor here. You could visualize the center conductor of a piece of coax as being like a hollow tube at higher frequencies rather than a solid conductor. And I'll get back to this in just a moment because I've got some graphics that really help to illustrate what's going on. So let's take a look at the center conductor for a piece of half-inch hardline cable. The nominal outside diameter is 0.109 inch. That's pretty typical. It's copper-clad aluminum, and the cladding is typically around 2.5 mils to 2.8 mils thick, or 0.0028 inch in this example. Now, understand that my figures are not to scale, because if you look at the end of a center conductor in a piece of coax, hardline coax, it looks like it's pure aluminum, but there's this really thin layer of copper on the outside. So, but I've kind of exaggerated it here to show what's going on. So we've got this copper cladding that's about just under 0.003 of an inch thick, and then the aluminum core is a little over 1/10 of an inch thick. So this would be what's going on with a piece of center conductor from half-inch hardline cable. So at 5 megahertz, again, we're looking at the cross section of the center conductor for half-inch hardline cable. So we got the aluminum core, and the skin depth at 5 megahertz is about 1/1000th of an inch. That's this pink area here.
So the pink area is where the RF is flowing through.
That's where the RF is flowing at 5. Most of the RF. There's a little bit that goes below that, but most of it is in that pink area at 5 megahertz. So you can see that there's still plenty of copper left over. It's not even getting into the aluminum. At 100 megahertz, which isn't that much higher in frequency, well, it is, but it isn't compared to gigahertz or 1.8. But here you can see that now we're down to 3/10,000ths of an inch. That little thin pink area is where the bulk of the RF is traveling at 100 megahertz. So you can see we've got all kinds of copper left over there. And so that means that we don't need to use a solid copper center conductor because we're basically just wasting it in coaxial cable. You don't need it as long as you've got that copper cladding. So now, let's go back to my hypothetical example of imagining the center conductor of a piece of cable as a hollow tube. So for this, what I've done is worked with an example that assumes we take a 100-foot length of center conductor from half-inch hardline cable. And at DC, so this is what you'd measure with your regular ohm meter, for that 100-foot length of center conductor, which remember is copper-clad aluminum, its end-to-end resistance is just over 1/10 of an ohm, 0.135 ohm. Now, when we talk about resistance in coaxial cable, typically we look at a parameter called DC loop resistance. And the manufacturers usually specify that over 1,000 feet. But in their spec sheets, you'll typically also find the resistance, the DC resistance of the center conductor and the DC resistance of just the shield. When you add those two together, you get the loop resistance. And the way to visualize how that's measured is take a 1,000-foot chunk of hardline cable, short circuit the center conductor to the shield at the opposite end. Then at the near end, hook your ohm meter up and measure between the center conductor and the shield. And then that gives you the loop resistance, the DC loop resistance of 1,000 feet. So what I did was just divide by 10. So I took the published DC resistance of the copper-clad center conductor for half-inch hardline cable. So that's what this leftmost graphic shows. So we got the copper cladding on the aluminum core, the end-to-end DC resistance at over 100 feet. And I just divided by 10 from the 1,000-foot spec. The DC resistance end-to-end is about 0.135 ohms, so pretty small. And then what I did was I looked at a table of wire gauges versus resistance for copper wire and said, what is the equivalent of this center conductor compared to solid copper wire in terms of resistance? So this 0.109 inch outside diameter copper clad aluminum's resistance at DC is approximately equivalent to a solid copper wire that's between 11 gauge and 12 gauge. So call it 11 and a half gauge, even though I don't know that anybody makes it like that, but it's roughly equivalent to that. So good size conductor. So that's pretty good at DC. Now at 5 megahertz, we can visualize our center conductor turning into a hollow copper tube. The black part here represents the inside of this hollow copper tube, and the outside copper colored here is just the wall of the tube, and we're looking at it end on. So here, the effective AC resistance over 100 feet of this now imaginary hollow copper tube, let me get this guy out of the way, is a little over 2 ohms over 100 feet. That is approximately equivalent to 23 gauge copper wire. So look what we've done, just going from DC to 5 megahertz. We've gone from the equivalent of 11 or 12 gauge copper wire to about 23 gauge copper wire, which is pretty small stuff. But what happens at 100 megahertz? Get this guy.
Yeah, so I mean, you really dramatically changed the composition of that wire, because 11 or 12 gauge wire can carry like 50 or 20 amps, actually. I think 12 gauge wire carries 20 amps, whereas 23 gauge wire is a really small wire that you would use for like small electrical circuitry. And that won't carry much more than maybe an amp at max if you're lucky. There's a totally difference when you go from DC to just 5 megahertz, and what can just even if you think about current carrying capacity. So if you look at that from like what's the resistivity, what's the resistance of that, the resistance goes way, way up. And this really starts to explain how the attenuation in coax cable starts to be impacted at higher frequencies. And I think that's something that really doesn't make sense when you think about it, because if you measure the resistance or attenuation of a piece of coax cable, it's very small, and you start to scratch your head and say, well, why does RF get attenuated so high when we are giving it such a big center conductor to go through?
Well, and it's not using that big center conductor.
Yeah, I know.
It's surface a little bit. Now we look at here at 5 megahertz, the equivalent thickness of the wall tubing. Or the wall of our imaginary hollow copper tube is about 1/1000th of an inch. That's the skin depth. So at 100 megahertz, we now have a copper tube, and the outside or the thickness of the wall of that copper tube is only 3/10,000ths of an inch. The effective resistance over 100 feet is a little over 9 ohms. That's approximately equivalent to between 29 gauge and 30 gauge copper wire, which is really
small.
Yes. At 870 megahertz, the thickness of the wall now of our imaginary hollow tube is 0.00009 inch. So the effective AC resistance is now almost 27 ohms over that 100 feet, and that's roughly equivalent to 34 gauge copper wire. So this is a big reason why the attenuation increases as the frequency goes up, because the effective AC resistance gets worse the higher in frequency you go. Right. And of course, you might be wondering, gee, is there math for that? And yeah, the answer is, yeah, there is. There's a formula for that.
So Jared Sanders asked, does temperature have any effect on skin depth?
Yeah, everything that I'm talking about here is at room temperature. The impact as the temperature changes will change this a little bit, because we know that attenuation in coax changes as the temperature changes. And I wrote an article years ago about that, and it has to do with the conductivity or the resistivity of the metal at different temperatures. And the way I like to describe it is, as the temperature goes up, the atoms in the metal are jiggling around a whole bunch more. And there's, if you visualize a piece of copper conductor, these an electron is zipping through it, and it goes a certain distance, and then it runs into an atom. And the more those atoms are jiggling around, the more that those electrons get slowed down. So the resistance effectively goes up as the temperature goes up. So the attenuation increases. And as the temperature drops, then the jiggling at the atomic level slows down and the electrons don't whack into things quite as much. So the resistance decreases. And that same effect does impact what we're talking about here in attenuation through coaxial cable. They're very, very closely related. So anyway, so there's how skin effect impacts coaxial cable attenuation.
Yeah, we got all the way down to the atomic level on this today, folks. So awesome job,
well, yeah,
Ron.
this is the effective this is the resistance or the effective AC resistance, and here you can see there's the frequency and conductor size and resistivity is in. Whoops, resistivity is in there too. So that yes, they're all very, very closely related, and there's some really good questions. Now let's wrap this up, and then if folks have questions, we can touch on those. So I think it's important to understand that what we talked about today, skin effect and skin depth and metallic conductors, are big parts, big parts of the coaxial cable part of our networks. And the discussion is focused primarily on coaxial cable, and it makes it easy when you talk about the center conductor. Same principle applies to the shield of the cable. Same principle applies to a splice. If you open up a splice, see the inside, you can see it behaves, or it's designed somewhat like a transmission line. Tap, amplifier housing, all those things play a role. So skin effect helps to ensure that the RF stays inside the cable where it belongs and outside stuff stays out, as long as the shielding integrity is not compromised for some reason. And of course, skin effect and skin depth are big reasons why attenuation in coaxial cable increases as the frequency goes up. So here's a question for people. Do you think it's important to not score the center conductor when you're prepping a piece of cable for connectorization? Why or why not? So if I've got this piece of cable here and I'm cutting the center conductor off with my pocket knife and I score the center conductor, is that a big deal?
So I made that joke earlier on, Ron, and we'll see if anyone drops a chat in there. But yeah, I made that joke earlier on. But they make really good cable prep tools for removing the shielding, the basically properly prepping coax cable, coaxial cable. Ron, sorry, I know that's the proper way of pronouncing it. Specifically, so it does not cause any damage to the center conductor. It doesn't create any scratches or damage or anything like that. But occasionally, technicians will maybe not have a proper equipment or not have it with them, and so they'll resort to a pocket knife or a tool like this one here. That's why I made that joke earlier about why we should be very careful about not damaging that center conductor or improperly connectorizing the outer shielding. And I think maybe this presentation really kind of drove that home about how little of the center conductor that RF is riding on, and if you do any damage, we're talking about hundreds or thousands, or even, it's even much smaller than that at higher frequencies, right? To 0.000000 of that center conductor is being used. So Jared says, after this presentation, it definitely drives home to use proper craftsmanship. So thanks, Jared. And Tom Ranson says, high frequencies don't jump. So that's awesome, that's right. Tom. So if you cut that outer conductor,
that's going to affect things at high frequencies. At low frequencies, yeah. When I was an installer back in the 70s, we used pocket knives to prep the drop cable for F connectors. And of course, the system where I started, the highest frequency was channel 13. So 220 megahertz, basically. All right, well, you score the center conductor, okay, not a big deal. But if you got a gigahertz for your upper frequency limit or 1.8 gigahertz, scoring that center conductor could be a big deal and have a negative performance on the RF particularly at the higher frequencies. Yeah. All right.
And Jared, Jared actually jumps back in and said because he says low frequencies can't jump, laughing out loud. High frequencies can't swim. But I think, so we let's just dive into that really quickly. When you score that outer conductor, so high frequencies can jump that gap, right? It's we have problems with high frequencies in water. We've covered that in other episodes.
Mhm.
Why wouldn't the high frequencies be able to jump a score in the outer conductor? Because I
Well,
think now we've kind of we kind of opened that
well,
up.
that might look like a capacitor at the higher frequencies. And depending on the depth of the score and the width of the score, the capacitance value is going to be changed. So now you've got a capacitor essentially in series. But if you visualize the current propagating along that conductor, it's going to go a little bit down this and possibly get into the steel, which has worse resistance. So the reality is you're likely going to increase the effective AC resistance by scoring that center conductor. And will the RF go through it? Sure, it will. Is it going to go through it as well as it did at lower frequencies? Not necessarily. Uh, so you don't want to score that center conductor because it could impact the performance at those much higher frequencies. You just, I mean, you're not doing lab calibrated scoring on that to say, all right, I'm going to put a 0.001 microfarad capacitor in series with the outer shield of the cable. Well, yeah, you don't know what you just did. And making things worse, if you get through that copper cladding, you've now exposed, in the case of the drop cable, the steel, and you've exposed the aluminum in the hardline cable, which now could be more susceptible to corrosion and oxidation. And you could get a mechanical breakdown there because of oxidation where you've gone through that metal.
Yeah. And let's also not forget that the downstream, while it could jump, we also have upstream frequencies that are much lower in frequency that the cable modem's transmitting on the upstream. So we're going to be impacting both high frequencies and low frequencies on
I don't
any.
think you're going to see as much impact at the lower frequencies because it's such a narrow score in the center conductor.
Mm-hmm.
The bigger thing is what are you doing to that copper cladding,
right,
and the RF at the higher frequencies. Yes, the RF will go through it, but
yeah. All right, and then Stryker says, I'm looking into getting into the cable industry. My home prep tools, since I run my own coaxial cables, are what the pros use. I use a Jonor tool UST 1596 for cable prep. So awesome.
Yep, use the correct prep tools. What you'll often find is that the manufacturers of connectors will specify certain prep tools for their products. They'll say this manufacturer and that manufacturer has these available. Use these prep tools when putting connectors on the ends of the cable. That's very, very important because it ensures not only the proper trim dimensions for the jacket and the braid and the dielectric and everything else, but it also helps to make sure that you're not cutting through things that you shouldn't be cutting through, like the center conductor.
Very, very important. All right, Ron, anything else?
In our last session, I promised that I would touch on modulation. In our next session, here we are, and I did a presentation on skin effect and skin depth. I don't have a slide in my existing deck for modulation, but I just wanted to mention for those who might have tuned in and said, all right, Ron, where's your explanation for modulation? And, what is modulation? When we talk about getting RF or getting information through our cable networks, we transmit RF, but how the heck can you use RF to transmit information, whether it's video or audio or digital data? And what we do is vary one or more characteristics of the RF signal as it propagates through the cable or signals. We can vary the amplitude, which is AM or amplitude modulation. We can vary the frequency of the RF signal. We can vary the phase of the RF signal, or we can vary some combination of the two. Single carrier QAM signals, for example, in the downstream, QAM or quadrature amplitude modulation uses a combination of amplitude and phase modulation to represent groups of ones and zeros that are called symbols. But that's modulation, and a more in-depth look at that is certainly a topic for a future session. But I did want to mention that because I did promise that I would touch on it in our last session. So for those who were curious, there it is.
Thanks, Ron. Thanks for that explanation. Jared Sanders says, just wanted to say, while I have caught a live video, I've been a MT for going on 3 years and have learned quite a bit from your content, Brady and Ron. We appreciate it. Thank you, Jared. We appreciate your comment.
Yes, thanks for the kind words.
Yes, absolutely.
We can never stop learning in this business. Never stop learning. And I've been in the business for 51 plus years, and I'm still learning. Never stop learning in this business. So
no, absolutely not. Myself, I've been just over 30 years, and I'm still learning from you, Ron, so I really appreciate it. And we very much appreciate your presentation today, Ron. I appreciate if everyone would subscribe, give us a thumbs like up, hit that notification bell so you get notified on upcoming episodes. We'll be back on next 2 Fridays from now, January 19th, I believe it is, episode 95. It's going to be back with John Downey, another DOCSIS Get Your Tech On episode. So, Ron, thank you again. Great episode today. I think we learned a lot about skin effect and skin depth. It should be abundantly clear to everyone. Stay away from these when prepping your cables, because that really gets under Ron's skin. So, thank you, Ron. Thanks, everyone. Until then, this is Brady Volpe and Ron Hranac signing off. Take care, all.
Cheers.